Assalamu alaikum everyone. Welcome to the course of Real-Time Embedded System. Today we are going to start lecture number 14, chapter number 5, and we are going to continue our memory section. And today inshallah we will finish off this chapter 5. Before I start today's topic, let's recap what we have discussed in our previous lecture. In previous lecture we talked about mapping techniques of caching. We talk about direct mapping, we talked about two-way set associative, we talk about fully associative cache mapping, and we also talk about cache replacement techniques in which we discuss random replacement policy, least recently used replacement policy, and finally we discussed cache writing techniques that were write through and write back techniques. In today's lecture we are going to discuss advanced RAM, its variation, and DRAM integration problem, and finally we are going to talk about memory management unit. So let's start it. So earlier we described DRAM, that is dynamic random access memory, as a type of storage device that use single transistor capacitor pair to store a bit. Because of such architecture, it results in high capacity and low cost. DRAMs are commonly used as main memory in processor-based embedded system. Okay. In order for DRAM to pace with processor speed, many variations of DRAM are proposed. So we use these variations of DRAM in order to keep the memory speed with processor speed. So first we have FPM DRAM, that is fast page mode DRAM. Then we have ADO DRAM, that is extended data out DRAM. Then we have SD and ESD RAM, that is synchronous and enhanced synchronous DRAM. Now in our basic DRAM, address bus is multiplexed between rows and columns. So this is our address bus, as you can see here. It is multiplexed between rows and columns component. Rows and column addresses are latched in sequentially by storing RAS and cache signals. So storing means just a signal. So we can latch our column address in the buffer and we can latch our row address in the buffer with the help of these two signals, which is called storing signals. Okay. Now refresh circuitry can be internal or external to the DRAM. So here we have refresh circuitry. This refresh circuitry requires storing signal, that is cache for column and RAS for row, and we require a clock signal. Okay, so this is refresh circuitry, so we need to refresh this and we also need to refresh this. Okay, these two components, column decoder and row decoder, and ultimately we are going to refresh this whole block. Stores consecutive memory addresses periodically, causing memory content to be refreshed. So we periodically store consecutive memory locations in order for memory contents to be refreshed, otherwise it will lose the data. So we know that our DRAM, our basic DRAM, consists of capacitor and transistor. So if we do not refresh the capacitor, there will be a charge leakage and we will lose the data. So this is our basic DRAM. Okay, so here we have data, that data is coming in, so we have data in buffer. Here data is coming out, so we have data out buffer. Here we have read, so for read we just are going to data out. Reading means just data out, whereas for writing we have bar and we have not here, so data in. So data in going towards the sense amplifier, whereas for data out, for reading, the data is coming out of the sense. And here we are going to access the column and here we are going to access the row. So for one row, one particular row and one particular column, we are going to access the word, okay, or one bit. So this is bit storage array, and here we are refreshing each row, and here we are refreshing each column. So this is column decoder, this is row decoder, and not every time we are refreshing, that's why we are using here mux. Okay, so multiple lines and single output. So sometimes when we are refreshing, we are not reading and writing. When we are reading and writing, we are not refreshing. So this is the basic architecture of the DRAM. Let's move on to next slide. So the first variation in our DRAM is fast page mode DRAM. As I've told you, we need these variation so that our RAM can match with the speed of the processor. Now, each row of memory bit is viewed as a page, so we can view each bit as a page. So row is viewed as a page. Page contains multiple words, so there are multiple words in a page. Okay, so it's just like this is our page and we have multiple words in it. Individual words addressed by column address. So if you want to access this, or if you want to access this, we need to know the row and know the column. Now timing diagram. Row represent page. 3-word read consecutively by sending column address for each. So we can read 3-word consecutively by sending the column address for each. So if we have like 3 column addresses and 1 row addresses, we can read 3 words consecutively. Extra cycle eliminated on each read write of word from same page. So because we are not using row, okay, so only once we are using row and then we are using column, column, column. So extra cycle, we can eliminate that extra cycle for row. So this is the RAS signal, that is the row signal, okay, and there is the cache signal, that is the column signal. So here we are reading the address of the row, here we are reading the address of the column, address of the column and address of the column, and we are reading these addresses at the rising edge of the cache. Okay, we are reading this at the rising edge of the cache, and then you can see here that once we have row and we have column, now we can pick up the data here. Now again, this is second word, row and column, second word, and then we have another column, so we can pick up the third. So we have spaced up the memory by saving the extra row addresses. So extra cycle eliminated on each read and write. So if whether you are doing reading here or you are writing here, so we are saving extra cycle eliminated on each read and write. So we do not need any extra cycle here, we do not need extra cycle here. We can read 3 consecutive words by sending column addresses for each. So that was fast page mode DRAM. Next, move on to next. So in this slide we are going to talk about another variation of DRAM, that is extended data out DRAM or EDO DRAM. It is an improved version of fast page mode DRAM. What we do here, if you go back to the previous slide where we have discussed the basic architecture of DRAM. So if we use extra latch before output buffer, now what happens? It allows storming of cache. So we have studied 2 signals, RAS and cache. So what happened? We can trigger the cache before data read operation completed. So because of this, we can have reduction in our read write latency, and we want our latency to become less so that we can have high throughput. So we can further reduce down our latency. So if you see here, we have, let me take a pointer here. So this is our RAS signal. So because we just need one row, and then we have cache signal for 3 columns. So at this point, when rest started to increase, that is our high clock, we read row address, and then at each rising of the cache, we read column address. Okay, here. And once we have row and column, we started to read or write the data. But important thing is that we haven't finished reading the data yet. Okay, we haven't finished the data yet. What we are doing, our cache signals start storing. So here you can see we haven't finished reading the data, but our cache signal starts storing. So we can save this time and read the next column address. So once we done with reading the next column address, we can read and write the data. So here we haven't finished reading the data, but what happens, we are reading the next column address because of this storing signal, so this space, what is this? This is our speed up through overlap. So we are overlapping. You can see here we are overlapping the column address reading. We are reading the new address, whereas we are reading the previous data. So this is extended data out DRAM. Let's discuss the last one. So the last type of variation is synchronous and enhanced synchronous ES DRAM. SDRAM latches data on active edge of clock. So we have seen that previously in both the variation we do not have any clock, but in synchronous DRAM we have active edge clock. So it means that we store and means read or write the data on active edge of the clock. So it eliminates time to detect RAS, cache and read write signal. So we do not need to detect RAS and cache signal. Rather we can work on the clock timing. A counter is initialized to column address by increment on active edge of clock to access consecutive memory location. So if you see here we have a clock. So on first clock we have RAS, we have reading RAS, storing signal, then we have cache. So once we have row and column, we are not going to initiate the cache signal and column here. Why? Because we are going to use clock in order to increment the column. Okay, so that's why we can read data and data. So we can read 3 words just with the help of single cache signal. So we eliminate time to detect. We do not have to detect the cache signal. Okay, rather what we can do, we can increment in the column on the basis of active edge. So a counter is initialized to column address. So we can activate a counter here on the column address, then increment on active edge clock to access the consecutive memory location. Now the ESDRAM is enhanced synchronous DRAM, which improves SDRAM. So we can further improve our SDRAM, that is synchronous RAM. So what we do, we add buffers, enable overlapping of column address. So what we can do here, if you go back to previous slide, we have studied extended data out. So we can overlap these column reading signals. Okay, so this is column address. We can move this data further back, faster clocking and low read write latency possible. So what we are going to do, we are going to combine this with our previous strategy so that there isn't some overlapping. So if we use buffer, so we can read the next address or we can compute the next address while we are reading or writing the data in the cache, as we have done in the previous slide. So that was about enhanced synchronous DRAM. So we are using clock here. So in this slide we are going to talk about the dynamic read random access memory integration problem. As we have discussed so far static and dynamic types of RAMs and brought up the benefits and disadvantages of each type. In this slide, we will describe the problem of integrating memory and conventional logic on the same ICs. SRAM easily integrated on the same chip as processor. So we can integrate SRAM on the same chip as processor. DRAMs are difficult to integrate on the same chip. Difficult chip making process between DRAM and conventional logic gates. Now, what is the goal of conventional logic IC designers? The conventional logic IC designer minimize parasitic capacitance to reduce signal propagation delays and power consumption. So their goal is to reduce the power consumption and propagation delays. Whereas the goal of DRAM designer is to create capacitor cells to retain stored information. So in DRAM, the goal is different from the goal of conventional IC designer. Integration process beginning to appear. So right now it is very difficult to integrate DRAM on the same chip as processor, but with the passage of time, integration processes are started to begin. So let's move on to next slide. So in this slide, we are going to talk about memory management unit. Duties of memory management unit includes handles DRAM refresh, bus interface, and arbitration. Arbitration means to settle the dispute, takes care of memory sharing among multiple processes, translate logic memory addresses from processor to physical memory addresses of DRAM. Now, modern CPU often come with MMU built in. Single purpose processor can be used. Either we can use single purpose processor for memory management unit, or in most of the modern system, the memory management unit is built on. The primary purpose of memory management unit is used to refresh the DRAM, it's used for bus interface and to settle down any problem that occurs. And it also takes care of memory sharing among multiple sources and translate logic addresses from processor to physical addresses of DRAM. So that was it. Thank you very much.